Hey y'all, as promised, I'm going to go ahead and do a quick castify on a couple of things. First, I'm going to talk about the Stemscopedia that you did today, and I'm going to go over just the first question. The second question, I'm actually going to take you on a field trip to my backyard. So just the first question first. So let's go ahead and open up the Stemscopedia. You're in Stemscopes right now. You've navigated there through Clever, and you've gone ahead and clicked Stemscopedia. By the way, if you see this concept attainment quiz and it does not say started if it doesn't say like turned in or completed or whatever, if it says assigned or started, you need to finish that and get that to me ASAP. All right, back to it. So we're going to go ahead and click Stemscopedia. All right, excuse me, Stemscopedia from Formation and Motion of Galaxies. The universe includes everything that exists, all matter, energy, space, and time. But how did the universe come into existence? People in every culture throughout history have attempted to answer this question, and scientists are no exception. How do you think scientists attempt to study and answer questions about the universe's beginnings? What kind of theories do you think scientists have proposed? What kinds of evidence might support those theories? Well, the Big Bang Theory. All matter and energy in the universe, contained in a volume of space that scientists have discovered, is constantly expanding. This expanding universe is similar to a balloon that's constantly inflating. The Big Bang Theory is the most widely accepted theory to explain the origin of the universe. According to this theory, the universe began as a very dense, hot, single point in space. Like I was talking about in class, that point of infinite density, that singularity, never happened before, at least not provably. From this point, the universe expanded rapidly. After the initial expansion, the universe cooled and matter formed. The universe continues to expand to this day. Okay, that's kind of boring and dry, but if you remember what I was talking about this morning, it wasn't like boom. It wasn't an explosion per se, because nothing got destroyed, right? It just spread that fast. Remember what sound it made? We call it the Big Bang, except for it was silent. Because remember, in order for sound to travel, there needs to be particles. Before there were particles, there was no sound. So the Big Bang was silent. Crazy, right? Take a minute and explore this picture. It's really, really beautiful. And you can manipulate it. You can go up and down. You can zoom out. And if you look at these right here, you can go up. That's the Milky Way. Beautiful. Or at least the part of the Milky Way that we can see. In the 1920s, a scientist named Edwin Hubble, Hubble Telescope, named after this dude, Hubble. Remember that, might be a test question. In the 1920s, a scientist named Edwin Hubble discovered evidence that the universe was expanded by analyzing light from distant stars. Scientists worked to try to explain these observations. The Big Bang Theory was not always the accepted theory of how the universe was formed. Another theory, proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi, was the steady state theory, which basically hypothesizes that everything that ever was is. There was no beginning, there was no end, alpha and omega kind of thing. Let's see. Hypothesized that although the universe was expanding, it was not changing because new matter was constantly being made, keeping the density of matter in the universe the same. Scientists worked to test both theories, and their discoveries have continued to support the Big Bang Theory and disprove the steady state theory, which basically is like more stuff making, and that's not right. All right, age of the universe. 14 billion years ago. The age of the universe. Scientists cannot directly observe the beginning of the universe. Well, duh, we're not around that long ago. How then do you think scientists can study the Big Bang? How can scientists know when the Big Bang happened? Take a moment to answer these questions for yourself. Because the theme song to the Big Bang Theory says so. The whole universe in a hot, dense place, then 14 billion years ago, expansion started. Wait, no? All right, let's find out how. Light years. Visible light is a form of electromagnetic radiation, or energy that travels at super high speeds through space in wavelength patterns. In fact, this energy is the fastest thing in the universe. In a vacuum, electromagnetic radiation travels at a constant rate of about 300,000 kilometers per second. It's the speed of light. Because the universe is so vast and light moves so quickly, light gives scientists a useful tool for measuring distance in space. So basically, it's like this. You're not going to get a really long ruler to see how far it is from here to the edge of the universe. You can't, obviously, right? So how do we measure it? And it's so huge, even the distance between here and like Betelgeuse, the star, to say how many kilometers or miles or something is it's just ridiculous. The numbers would be too huge. So a new way of measuring distance is the light year. So let me say this again. We measure distance in light years, not light year time. It's distance. It's how long light travels or can travel in a year. So if you think of turning on the flashlight and it instantly hits the other side of the room, right? How fast light travels, and yet how long it would take to get from one point to another. A light year measure of distance. All right. Here we go. A light year is the distance light travels in a year, about 9.5 trillion kilometers. If a star is 4 light years from Earth, light from that star takes 4 years to reach Earth. If a star is 4 million light years from Earth, light from that star takes 4 million years to reach Earth. This means scientists are, in a sense, looking into the past when they observe electromagnetic radiation in space. Scientists can estimate the age of the universe by observing the universe's oldest stars and the intensity of their redshift. A redshift occurs as an object moves farther away from the source. It actually appears essentially red. And it has to do with the speed of the waves and infrared energy. And we'll talk more about that kind of energy later on in the year. Redshift occurs as an object moves away from the source of light and shifts towards the red end of the electromagnetic spectrum. This means the light emitted has a longer wavelength. If it was moving toward, which is not, everything's moving away, but if theoretically it was moving towards, it would appear purple. Scientists can use these observations to calculate the rate of the expansion of the universe and to work backward to determine when the expansion first began. It's kind of like if you know how fast a car is moving and you know how long, if you know how fast it's moving and you know from where it came, then you could kind of estimate when it began at that point. So using this method, scientists have estimated the universe is about 13.7 billion years old. In other words, the Big Bang is estimated to have occurred almost 14 billion years ago. All right, getting technical, remote sensing instruments. If you've ever driven between here and New Mexico, you'll sometimes see this sign that'll say, this way to the Very Large Array. It's a very thoughtful and creative name of a place that has these huge telescopes, these radio telescopes, and they're all on like tracks and they move around. It's super, super cool. If you ever have a chance and you see Very Large Array, hey folks, let's stop. It's pretty cool. It's pretty cool. They have a gift shop. Anyway, remote sensing instruments are essential for studying far reaches of the universe. Many objects are too distant or dim to detect with visible light. They give off low energy forms of electromagnetic radiation, such as radio waves, microwaves, and infrared radiation. Scientists can use large radio telescopes, similar in appearance to large satellite dishes, to detect radio waves from space. All right, so here's our first question. Try this. This photo, and yes, that's an infrared photo. This photo taken by a satellite in 2003 shows the most distant parts of the universe as observed from Earth. Okay? The different colors represent differences in temperature, which correspond to different densities of matter. For instance, red and yellow are hotter. Dark blue areas are cooler. These densities later become stars and galaxies. This discovery won the 2006 Nobel Prize in Physics. So take a few minutes to study it. Interesting. Okay. Circle the areas in the image that you think indicate areas that contain more matter. Box the areas in the image that you think show areas containing less matter. Notice that most of the image is the same color, meaning most of the radiation is the same temperature. Write a paragraph explaining, in your own words, how this observation provides evidence to support the Big Bang theory. Well, let's look at it. The hotter it is, the more matter is there, right? Because if it's cooler, it means that the matter is moved away from that space. Does that make sense? Because if it's matter and it's super, super hot, and it's moving away from that space, then that place left behind is going to be cooler. So let's look here. It says put a circle that's going to contain more matter. So we're going to come up here and we're going to put a shape. And we're going to circle like that. Or you can, there's another way to do it. I think it's this one. Is it that one? Yeah. Well, anyway, so you got to go ahead and circle where you think it has the most matter, which is going to be the hottest. And then put a square on where it's coolest. Something like that. You could go ahead. There's a couple other places. You could put another little square here or a square over here. But for the most part, I'm going to move it for a second so you can see. See all the red and yellow? That's showing it's really hot. And the hotter it is, the more matter is there. So one day, that might be new galaxies. All right, so I'm going to go ahead and cover that spot. Okay, you with me so far? All right, now I'm going to come down here and I'm going to write a paragraph saying why this is evidence for Big Bang Theory. Well, let's see. It's all pretty equally distributed, and it all seems to be moving away from this cool center. So maybe I would say something like, from Earth, you can see that, that the universe is expanding away from each object. I might say light is traveling at predictable speeds to support Big Bang Theory. Whoops. Now your answers obviously are going to be different. How does this support it for you? You might say something about how all the energy seems to be spread out pretty equally, or it's all moving away from some point, or maybe you're saying everything has equal distances away from each other, showing an equal spread. Any of that is evidence that this supports the idea of everything moving away from each other. All right? So that's how you're going to answer this. Again, your answers might vary, and that's fine. This is what do you think, and how do you think? All right. Now, I'm going to read this last part, and then we're going to move on to our field trip. So, gravity. The law of physics, including gravity, came into effect during the Big Bang. In the first seconds after the Big Bang, gravity caused matter to come together to form particles from which all components of the universe are made. From its birth to the present, the universe has changed tremendously. Huge pockets of gas have been pulled together by gravity to form stars, and in turn, those stars have been drawn together by gravity to form families of billions of stars called galaxies, and stars born long ago developed, aged, and died. And this process is still going on today and will continue into the future. Stars are large objects in space that generate their own energy. Almost everything you see in the night sky with your unaided eye is a star, except for an occasional planet, or a week or so ago you were able to see the International Space Station. But for the most part, most of the things you see at night are stars. A star is a huge ball of gas that produces its own energy through nuclear reactions in its core. Light is the most obvious form of energy produced by a star. However, stars produce many other forms of energy, such as infrared, radiation, heat, ultraviolet radiation. Gravity holds together the particles that make up a body of a star. In other words, a star is so massive that it's held together by its own gravity. The most commonly accepted hypothesis of star formation is that stars form from vast clouds of dust and gas called a nebula, or nebulae, if there's more than one. The force of gravity is strong between the countless particles of dust and gas, and gravity causes the cloud to condense and eventually collapse upon itself. As the center of the cloud becomes denser, it starts to spin and heat up. And gravity pulls more gas and dust particles into this hot spinning mass, and it continues to do this for millions of years. And finally, the matter becomes so hot that nuclear reactions occur. Remember me talking about nuclear reactions? That fusion, that bonding together at the nucleus of an atom. And that nebula then becomes a star. All right. Now, I want you to read on your own talking about the kinds of galaxies. There's 3 primary kinds of galaxies, and we'll talk more about this in the coming days. A spiral galaxy, that's like the Milky Way. It looks like a spiral. An elliptic, which is kind of an oval shape. An elliptical galaxy, and irregular, which is just kind of these like clusters and clumps of stars. And it could be because the massive galaxies on either side kind of pull them into irregular shapes. But again, we're going to read about that and talk more about that in the coming days. So now I am going to take a walk outside and I'm going to take in a field trip. So I'm going to stop this Castify right now and I will see you again in a few minutes.